Welcome to the lectures on digital control systems. As a continuation to our previous lectures, we can see that we are working on the state space analysis of digital control systems, and in that we are going to discuss today controllability of a state space system, where let us consider a linear time invariant discrete time control systems given by equation x of k plus 1t is equal to g into x of kt plus h into u of kt. Let us consider this state equation where x of kt is our state vector. X of kt is the state vector. It is a vector of n dimensional, right? It is an n by 1 matrix if you write it in the matrix form, and u of kt is the input vector, where let us say it is having its dimensions as r by 1, right? So this is a state equation, and we need to understand whether this state equation is completely controllable in all over its states, right? So any state vector, if you can consider x of kt or x of kt, you can say this is an n-dimensional system. N-dimensional system or n-dimensional space. It conquers all the n-dimensional space, right? X of kt. So in this n-dimensional space, it is necessary for us to find out whether the system is completely controllable or not, right? What do you mean by controlling any state variable? That is, x of kt will have n state variables that can be represented as x1 of kt, x2 of kt, so on, xn of kt. Now this is an n-dimensional system or a vector, right? You have n dimensions, or you can say if you start from 0 here, let us say if it is x1 of kt here, x2 of kt here, x3 of kt, and so on, xn of kt, you can say that it is covering all n-dimensional space. If you consider only two variables x1 and x2, then it is a two-dimensional space, right? Like x and y axis that you have. So entire x and y axis from 0 to infinity, or x2 also from 0 to infinity, what is happening in that, and whether it is controllable or not is what we are going to see in this controllability of x of kt, or the state equation. So in this n-dimensional space, we are going to find out whether we are going to control the entire state variables. Then it is called as complete state controllability. Complete state controllability. Right. So the heading now changes to complete state controllability of a state equation. Now we have n dimensions and all state variables must be controlled. Now how do we control all these state variables is what we will have to find out by knowing what is the input vector u of kt. Now this input vector must be unconstrained, or this input vector must be unbounded. It must be unconstrained or it must be unbounded. We should find out some input vector which will try to take this system. What is meant by controlling? We want this state variables x of kt, all the state variables, which is an n by 1 matrix, right? All the state variables x1 of kt to xn of kt to be transferred from one state to another by the help of the unconstrained input vector without any problem, right? So here every state variable must be in a position to be transferred from any initial x of t0, let me say x of t0, the initial state, any arbitrary initial state. It can be anywhere in the n-dimensional space. Arbitrary initial state of any system to x of tf, the final state, or you can also call this as any arbitrary desired state. Right. So we have this, we should be in a position to transfer the system state from any arbitrary initial state to any arbitrary desired state in that n-dimensional space which we have already discussed in our just a few minutes back, x1, x2, x3 and xn, for example. In this n-dimensional space, anywhere here, if my initial state is here, I should be in a position to transfer this to some other x of tf. This is x of t0. T0 is the initial time and tf is the final time, and this should happen, the transfer must happen within a finite time period. Finite time period. It should not take too much of a time to transfer the system state from one state to another. Always in control systems we try to consider that the response time must be as small as possible. Here the finite time period is our criteria. Within a finite time period we should be in a position to transfer the initial state, the state of the system from any arbitrary initial state to the arbitrary desired state. How do we transfer all this? How is this transfer happening? This entire process is happening within a finite time period. How is this happening? By the help of this input vector. We require some input, an input vector to transfer all these things. Only one input may not be possible for us to may not be sufficient enough for us to transfer all these state variables, n state variables from one state to another. So we may require a series of input vectors. So this input vector may be a scalar quantity, but you need to have n different scalar values, right? Or it can also be a vector. Right, it can be u of kt can be a scalar quantity or a vector quantity. Even once input signal is sufficient for all these state variables to be transferred from initial state to final state, or you can have a sequence of unconstrained control signals to transfer all the state variables from one state to another. But here in this process, what we require to understand is we need the input vector to be very importantly, we require input vector to be unconstrained and unbounded. We don't want any input vector which is bounded in nature, and it is also important that u of kt is existing from 0 to t, or kt less than or equal to t less than k plus 1 t. Right. So it is because we are going with the discrete time control systems, u of kt must be existing in this region. Right. For any value of k, and k is ranging from 0, 1 to so on n minus 1. Right. So if I substitute k is equal to n minus 1 here, n minus 1 plus 1 nt. So nth dimensional, we want all n sampling periods to be considered. Whichever n you are considering, you can go up to that point. Now there is one more important point that need to be considered here. If any one state variable out of all these n state variables is not depending on the control signal, then the system is not controllable. You cannot say that system is completely state controllable. Right. So this is what we need to understand. That is the controllability. Now by definition you can say that in any linear time invariant discrete time control systems, the transfer of the state vector from any arbitrary initial state to any final or arbitrary desired state within a finite time period by the help of an input vector u of kt, which is unconstrained and unbounded, then the system is said to be completely state controllable. Hope you all understood this state controllability. Right. So with this, there is one more point called reachability. And here in this, you can also say that you can start anywhere in the n-dimensional space and you can also come down to 0. This is one peculiar case. The final desired state can be an origin, right? It can be origin. I have written 0, 0 because I am just considering a second order system, right? So 0, 0 is a origin. So from arbitrary initial state anywhere in the n-dimensional space to origin. Right, so final desired state can be origin. This can also be done, and from origin to any other value can also be done. Now this is what we are trying to understand, and now in this case we can say that, we can understand that if any system, a similar case, from origin to any other final arbitrary desired state, if it is possible for us to transfer, x of kt from origin to any other final desired state, then it is called a reachability. Now we will understand this. What is the difference between reachability and controllability? Both are one and the same. Literal meaning it is one and the same. That is transfer of system state vector from any initial state to final state, or that by general broader sense you can say that reachability and controllability are one and the same. But peculiar if you go deep into the concept and try and understand what is reachability, you will understand that any system, if at times the system, if it is controllable, it cannot be reachable. It may not be reachable is what I am trying to say here in this context. Right. Let us say what is this? But reachability is a concept where your initial state is origin and you are trying to reach a final desired arbitrary state. Right. So we are trying to see that by the help of an example. Let me give you an example of x1 of k plus 1 t, x2 of k plus 1 t. I will take a second order equation. Right. Let me say the G matrix is 0, 0, minus 1, 1 and x1 kt, right, x2 kt. You know what is kt? T, it is time period, sampling period, and u of kt. Now t can be neglected here because while writing this equation you need not worry about t. Now let us say if you are writing these two equations separately in the equation form, x1 of k plus 1, I have neglected t here, 0 x1 kt and 0 x2 kt and 0 ut. It means that x1 of k plus 1 is 0. Then x2 of k plus 1, you can consider this here as minus x1k plus x2k plus uk. Right. Now from any initial state, any arbitrary initial state, now the final state is, let me say final state is origin. Final state is origin. Right. And how is it possible for us to, how many steps are required for us to transfer this state based on these equations to origin? How many steps are required? Just consider here, you can say this is origin here and the final state is origin in the sense x1 of k plus 1 is 0 and x2 of k plus 1 is also 0. Right. So how many steps are required for us here? You can say x1 of k plus 1 is already 0. So x2 of k plus 1, if I equate it to 0, what will happen here? Then here k is, if you consider k is 0, when k is 0, that is first instant, that is within one sampling period, you can just transfer x2 of 1 is equal to minus x1 0 plus x2 0 plus u of 0. Right. Now if this is equal to 0, what is happening here? x1 of 0 minus x2 of 0 is equal to u of 0. right? So at the first instant, by this control signal, you can transfer the system from, therefore you require only one step. Within a single step you are able to transfer the initial state to final state. The final state is origin for us here. Now this is controllable, you are able to transfer this. Now if I consider, then the system is completely state controllable because of this situation, right? Now let me see what is reachability. Reachability is the initial state is origin. Initial state is origin, that is x1 of 0 is 0 and x2 of 0 is 0. Now in this case, now x1 of 0 and this is k is equal to 0. When I substitute k is 0 here, I have x1 of 0 plus 1, that is x1 of 1 is equal to 0, and x2 of 1, what is happening to this? x2 of 1, based on this, minus x1 0 plus x2 0 plus u 0, that is minus x1 0 plus x2 0 plus u 0, and these two are zeros already for us. Now what is x2 of 1? It is u of 0, which is not equal to 0. Right? U of kt is a piecewise constant, piecewise linear constant. Right? Scalar constant, you can say x. So u of 0 is not 0. If u of 0 is there is no possibility for us to convert or transfer any system state from one state to another, system equation from one state to another. Therefore here x1 of 0 is 0. But x1 of 1 is 0, but x2 of 1 is not equal to 0. It means that you are not able to transfer. x2 of 1 can be transferred, but x1 of 1 is equal to 0. It is staying there wherever it is, right? We are not able to control the state variable, first state variable x1, right? So this is called reachability. We are not able to reach, so this is not reachable. You can say this as it is not reachable, right? So at times you can say that if a system is completely state controllable, it need not necessarily be reachable. It may be not reachable, right? So these two conditions must also coexist in order to say that the system is completely state controllable. Right. So with this in mind, let us go deep into the controllability part of the lecture, where we can see what is the condition, necessary and sufficient condition for us to see whether the system is controllable or not. The system state is completely state controllable or not. Now based on this equation, what is the solution for this equation? In our previous classes we have understood what is the solution for this equation. X of nt, let us say x of nt is equal to g power n x of 0 plus sigma j is 0 to n minus 1 g power n minus j minus 1 h u of jt. This we have already discussed in our earlier classes, right? So let me say we are having this as x of nt minus g power n x of 0, right? And to the right hand side I am putting this to the left hand side, and to the right hand side I will just elaborate this. When j is 0, what is happening to this function? G power n minus 1 h u 0 plus g power n minus 1 minus 1, it is n minus 2 h u 1t plus so on, g power n minus 3 h u 2t plus so on plus the last variable is g. When j is n minus 2, n minus 1, n minus 2, it is g power 1 h u of, what is the value of j? N minus 2 t plus g power 0. When j is equal to n minus 1, it is n minus 1 minus n minus 1 it is g power 0 h u of n minus 1 t. Now you can just simply write this equation. Now this is a thing which is existing in our n-dimensional space, right? This is the initial condition and this is the final. So what is the time taken between these two is also considered here, and x of nt is the final state, x of 0 is the initial state for us, for example, for us in this condition. And now if you represent this in the matrix notation, you can say that u n minus 1t, if I consider u n minus 1t, n minus 1t, u n minus 2t, right, so on, u 2t, u of t, u of 0. For example, if I write it like this and represent this in this form, in the first form, I am coming from the back, so h is our first h into u of n minus 1t, h into u of n minus 1t, right, and I will just divide this, gh is the next term into u of n minus 1 2t, so on, right, g power n minus 3h, g power n minus 2h, I will write g power n minus 2h u of t and g power n minus 1 h into u of 0, right. So this equation can be written in this form, right. It is a matrix notation, and you know what is the equation? This is an r by 1 vector, this is an n by 1 vector, we know this is n by n, this is n by 1, so what is h? N by r, h is n by r, right. So we can have this as n by r, this is n by n, and h is n by r, so you get here n by r, the combination gives us n by r, and similarly you will be having all the values as n by r, and this is 0, 1, 2, 3, so on, n minus 1, so this is n by 1 vector. So you will get an n by 1 vector without any difficulty. The dimensions are all satisfied here, right, without any hassle. So you can see this, consider this values, and now this matrix can be considered as the controllability matrix. Controllability matrix. Right. And what is the condition here for us? The controllability matrix, which is of order of n by r, which is of the order of n by r. The rank of this matrix, rank of the controllability matrix, controllability matrix can be given in the notation as QC. Rank of QC must be equal to n. Right. So n by r, it is having n dimensions, therefore rank must be equal to n. If the rank is not equal to n or less than n, then the system is not controllable. If the rank is equal to n, the system is completely state controllable. Right. So complete state controllability, the rank of the matrix, controllability matrix, must be equal to n. Right. So what is the controllable matrix here? H, gh, so on, g power n minus 2h, g power n minus 1h. So every term you are having g pre-multiplied with gh, right. So you can have this as the controllability matrix, and here already, which I have discussed, u of kt, if it is a vector, we have no any problem, we can directly find out what are the vectors. You have the vector here completely, and this vector can be helpful, can help us in transferring the system state from any arbitrary initial state to any arbitrary final state, desired state, within a finite time period. And how much time is taking for us? 0 to n minus 1, that is n sampling periods. N sampling periods right? N sampling periods is sufficient for us to transfer the system state from initial state to final state, and provided if the rank of this matrix is n, then the system is completely controllable. When u of kt is a vector, then you will have n sampling periods, and if u of k t is a scalar quantity, then it is necessary for us to identify n number of scalar control signals, n number of scalar control signals to transfer the, because you require n number of scalar signals, u of 0, u of t, u of 2t, and not all may be the same. Therefore, scalar quantities, scalar signals, both they are different. Therefore, you need to find out, identify some n control signals which are unbounded and unconstrained, right? But if u of kt is a vector, you will have n number of sequences, n sequences, different sequences can be obtained in a vector, right? But here in this you have, when u of kt is a scalar, you have only one sequence, because you can find out only one sequence, and to help us in transferring the system state from initial state to final state within n sampling periods. Now, what is the definition in terms of controllability matrix for complete state controllability? In any linear time invariant discrete time control systems, if the rank of the controllability matrix QC is n, then the system is said to be completely state controllable. That is what is state controllability. Now let us see what is output controllability. Now we have this equation, and we need to find out what is happening in this. I require these two equations again. Let us consider the full equation for us. What is our x of k plus 1t is equal to g into x of kt plus h into u of kt, and y of kt is equal to c into x of kt. Now this is our state model equation, which is our output equation. Now it is not complete state controllability, it is complete output controllability. Now let me say, if controllability in the state is possible, complete state controllability is possible, it doesn't mean that it is not necessary and sufficient to say that the output is also controllable. By other words, you can say that if complete state controllability is possible, complete output controllability may not be possible. This is one peculiar case here. So for that, what is the condition we need to find out? Now you have this y of k plus 1t, so x of k plus 1t is g x of kt plus h u of t, and y of kt is equal to c into x of kt. Now let us say, what is by definition we have the x of nt is equal to, what is the solution for the state equation? It is already given, g power n x0 j0 to n minus 1 g power n minus j minus 1 h. Sir, stop.